This is lecture 11. Let's begin with the summary of the previous lecture. In the previous lecture, we started to think about the multiple qubits, and then to think about the multiple qubit, we should first get back to our familiar concept of single qubit. And in the early lectures, we generally assume that each qubit will have its own vector space, or more specifically Hilbert space, meaning that it is a good linear space with the well-defined concept of the inner product. And then what we can do is we can combine more than one qubit together. And then in that case, because each of the qubit carries its own Hilbert space, so what we do is combine multiple Hilbert spaces to create a single new Hilbert space. Because we know that in quantum mechanics, according to three postulates of the quantum mechanics, the first postulates say that the um, quantum state of some physical system. Well, probably in the original in one of the previous lecture, I might say that I was just using the quantum state of a single particle, but that's only because I wanted to make sure that it is not too confusing. But more in more generalized term, the quantum state, not only the single particle, but entire quantum system. Because as we consider a more complex system, then yeah, whether we are just think about the single particle or complex system composed of many particles, yeah, they should still behave the same way. And then in all those cases, the quantum state is mainly described by a vector in a well-defined Hilbert space. So because if we don't have to think about multiple qubits, then we can just think about a single qubit, and then the Hilbert space will be simple. But once we decided to think about multiple qubit, then we have to consider the a more complex Hilbert space composed of the more basic Hilbert spaces. And then the mathematical tool to combine those multiple Hilbert space was the tensor product. So even though the terminology might sound a little bit scary, the way it is combined is quite straightforward or simple. And then the notation of the tensor product space is generally represented by in this notation, and each of the vector space represent the corresponding vector space of each of the qubit. So yeah, in this case, we are only considering two qubits. But if we are thinking about multiple qubit, then the space will be also extended with more tensor product of the spaces. And then the first thing we then for us to claim that this is a vector space or Hilbert space, then we should be able to define the vector inside that space. And then the way this new space is composed of vectors, many types of vectors, but those vectors are either directly combined two vectors, and then well, yeah, for this tensor product of two Hilbert space, yeah, then in that case we are just um, selecting one vector from one space and another vector from another space, and then we just put them together with this tensor product symbol. Then this is this kind of all of this kind of combination should belong to this new combined space. However, this is not the simple sum of those types of vector, because now this new vector space also satisfy the property of the vector space, which and then one of the important property is the closure, meaning that the linear combination of any vector in that space still should belong to the original space. So yeah, such kind of requirement is called as a closure in some situation. So not only this kind of combination, but not a combination meaning that we select a well-defined vector in this in this vector space and another well-defined vector from this vector space, but we can also think about the linear combination of these, which cannot be directly combined constructed by only just writing this way. And in some of them case, some of the so if you cannot simply write down as a simple tensor product like this one, and then such kind of quantum state is generally called as an entangled state. And then we will discuss the property of the entangled state in next lecture. So for the time being, just be aware that there are more vectors than you can just think about just by combining these two vectors. And for a good vector space, we also need to define the linear operator. And then the way we can construct or define the linear operator in this new vector space is quite straightforward. Similar to the vector in this new space, we can also think about the linear operator corresponding in linear operator in from this original space and another linear operator from this vector space, and then just combine them together with this tensor product notation again. And then this is not the only option, but we can also, similar to the vector, we can also think about the linear combination of these these primitive linear operator or these primitive combinations. So those are all well-defined linear operators. And then we also need to define how this new linear operator will act on the vector in this new space. And then in the last lecture, I emphasized that even though this kind of expression might look a little bit scary or look complicated, you can just think about each of these tensor product notation as a partition. So for this case, it was only a two combination of a two vector space, but we can always think about more vector space like this one, and another space like a combination four vector space. I don't know. Maybe like this one. Then in this new vector space, there will be more than then the vector in that space should be also expressed in this way. Something like x, and then another vector like a or whatever. And then we can also think about the linear operator acting on that vector space. So then the linear operator itself should be also extended to include more options, more the linear operator in this new space also should be the tensor product of the four different four operators coming from the original vector space. And then in this case, if this kind of linear operator works on this vector, the combination rule or the application rule is quite simple, as I mentioned. So we can always think that, well, this is just a partition like this one, and this is also the partition like this one. So the first operator in the first the operator in the first partition will work on the vector in the first partition, and then the second the operator in the second partition will work on the vector in the second partition, and so forth. So those are the quite straight forward rules. So don't be scared by just with this notation. And also still it might not be quite straightforward to imagine about the tensor product. So and then because this is a good vector space or linear vector space. So in principle, everything can be also represented in terms of the matrix. And then I also showed you that how we can combine each of the primitive matrix to express the matrix representation of the tensor product result. Finally, to be a good Hilbert space, which means that a vector space with the inner product, then we need to also define the inner product. And the way the natural extension of the um, inner products in the primitive vector space is just doing this way. Yeah, so similar to the linear operator rule, what we have to consider is the bra vector corresponding to this new space would also look like this kind of tensor product. And then in this case, similar to the linear operator combination rule, yeah, what happens is we should just combine the bra in the same partition to the so we have to apply the bra to the vector in the same partition. So the bra vector will be combined with the cat vector in the first partition, and then the bra vector in the second partition will be combined with the cat vector in the second partition, and so forth. So those were the rules. And then today we will now we have a mathematical tool to deal with more than one qubit. So let's now consider some quantum circuit. Before we start to think about many different types of quantum circuit, let me point out something which might be very important when you are comparing the quantum circuit with the classical counterpart. Um, the most important, or maybe the most confusing part, is the wire in the quantum circuit. Even in the quantum circuit, we frequently use this kind of wire looking like thing, and then we might have some single qubit gate, and then some multiple qubit gate, and then another qubit, another a single qubit gate, and so forth. So all of these are just to go, and then there might be another wire, another qubit, and also it might be connected to something else, or it might be even represented by some other some more generalized operator like this one. So yeah, this might be a very typical shape of the circuit. And then when I just draw the circuit like this, and then if you're very familiar with the concept of the typical circuit in the electronics, then you might think that, well, yeah, we have some kind of gate, and then these gates are the physical object, and then there is some kind of wire, and so forth. And that's not the case. For the quantum circuit, if you remember that when I when I described that there are um, a little bit ambiguity in the terminology of the qubit, and then qubit sometimes may mean the information stored in the quantum memory, and then some other cases qubit simply means the physical quantum memory by itself. And then if this wire somehow represent the time evolution, or the change in the time of the qubit information. However, on the other hand, each of these lines also represent, so each of these lines corresponds to physical quantum memory, or physical qubit quantum memory. Yeah, so yeah, that's probably where the confusion comes from. And then if I also have to somehow classify different types of the qubits, the first big classification is whether it is photon or the rest of the qubit. And then so if I just think about what happens with the rest of the qubit, then this kind of circuit exactly represent the time evolution of the information stored each of the qubit. So yeah, here I just drew the circle to represent some kind of physical memory, and then the shape of this one simply means that what happens as the time goes on. So the memory, quantum memory, somehow stays at the same location. And what really happens, and then this, what this circuit represent is the history of what will happen in the what will happen to the information stored in this quantum memory. So you don't get confused if you see this kind of circuit shape and then expect that we will actually draw the circuit. So there is, or you will wire the circuit. There is no such kind of thing. For the photon case, it is a little bit different story. For the photon, generally because the photon should fly away. So yeah, you remember that laser is one type of the photons, and then so laser actually flies away. So in that case, if we have three different photons, then in that case to implement this one, it is no more no more the time, but it might be a space. So the photon is actually flying like this one, and the first photon might pass through some of the optical component, yeah, which works as a X gate or whatever gate, and then the next time the photon flying here and then the photon flying here might do some kind of limited interaction. I said limited because this is not directly um, this is not perfectly correct, but in principle, yeah, we can somehow, yeah, you can imagine that the photon is flying, and then, yeah, in that case, you might think that the physical qubit is passing through the gate, but the rest the rest of type of the qubit, they don't actually go through the gate. But what happens is we apply the action corresponding to X gate or U gate or CNOT gate or whatever gate. We apply the action corresponding to this gate on these qubits. So yeah, there is some conceptual difference between the photon quantum circuit and then um, the rest of the type of the circuit, the rest of the type of the physical qubit. But that's a little bit of too much of detail. But my point is, wire is not, even though we just draw the wire like this one, it is not directly exactly the same as the wire you'd expect with the classical circuit. So yeah, based on so as long as you don't get confused, let's talk about the quantum circuit. The first type of the circuit I want to show you is what is corresponding to swap in the programming. So yeah, what do you mean? Yeah, let me think about the swap issue in the typical programming, and then yeah, you can see the difference or the similarity between the quantum circuit and the classical circuit. Well, yes, swap problem is the following. Yeah, you might start with some variable A and B in programming, and then yeah, you might store some value of A, capital A. Yeah, this might be I actually mean the some real value or some integer value A and B in each of the variable. Then the next thing is after some calculation, or this might be the situation in the middle of the programming, and then you want to change the value stored in these two variable. For example, yeah, you might have variable. Sorry, not capital A, but you have variable A and variable B, and currently the A value and then capital B value is stored in these two memory, and then eventually you want to swap the value, so such as you want the value B and then value A will be stored in each of these two memories or two variables, and then the simplest very brute force method to implement this one is just a oops, is that you might just declare one more um, variable, and then you might just store that the value. Yeah, so you by just declaring another variable c, then you can store the value stored in the a. Yeah, so this value will go to the here, and then you will move the value stored b into a, like this one. And finally, you would just move this one so that, yeah, it will go like this one, and it will be just replaced by the value a. So that's one way to, yeah, swap the value stored in these two variables. And then, yeah, but this was not the best way you can do, because when I learned programming in my college, yeah, one of the issue, yeah, people wanted to solve, or, yeah, one of the challenge was to minimize the use of the memory as much as possible. And is this the best way you can do? Yeah, because in this case you need three different variable, and the answer is now. There is actually one clever way to do that. Yeah, so instead of declaring um, three yeah, let me redraw this part. Yeah, instead of declaring three variable, we can still use only two variable to achieve what we want. The way the way it goes is the following. So instead of using the third memory, what we can do is first add the value um, uh, um, first add two of these values stored in these the two variable, and store the summation into the b variable. And then what we do is um, store the value and calculate the difference between b and a, and store the result into a. And in this case, because b is b plus a, and then if we subtract to a, then it will be b. So the value of b will be stored in here. And finally, if we do the b equals b minus a, then what we do is we are subtracting b from the total of these. So if I subtract b from this, then it will be just a. Yeah, so like this one. Yeah, so this is one clever way to implement the swap, and then you save the number of the qubit, and not the qubit, but the number of the variable we need. But a similar situation can also be similar concept can be also used for the quantum circuit. So yeah, with the quantum circuit, what the way, let's say that we have two qubit. Yeah, so there is two qubit 1 and qubit 2, or yeah, let's say, yeah, a and b qubit. Yeah, a and b qubit, and we want to um, swap the qubit information stored in these two qubit memory. So in that case, one way to implement such kind of situation is by using this kind of three um, cascaded gate, like this one. And then the reason this kind of gate implements the swap is the similar to what we saw with the programming example, yeah, like here. And then, but yeah, because we need different notation, so let's think in terms of the quantum memory, quantum gate. So if you remember um, the CNA gate, then CNA gate typically works in this way. If we have control qubit and then target qubit, and if we apply the CNA gate between these two types of the qubit, then what happens is the value stored in the control qubit is not changed, but the target information stored in the target qubit is also replaced by this kind of value, and then this means the XOR gate. If you are not familiar with the notation, yeah, so XOR means that if the two value uh, in the XOR are the same, then the result of the XOR gate is 0. While if only one of them are um, 1 and another one is 0, then the result is 1. So that's why it is called as XOR, or in more full name is the exclusive OR. So this OR does not allow to have both of the input to be 1. Yeah, so only when one of them is 1, yeah, so exclusively only 1, then this the result of the XOR is 1. So yeah, that's the notation. So let's think about what happens here. So here we can represent that at this point the quantum state looks like just a comma b. And what happens right after the first SNU gate? So what happens is we can use this notation, and then it will be just described by or expressed by in this way. And now, yeah, to think about what happens at this point is that then in this case the second qubit works as a control, and the first qubit works as a target. So this kind of notation should be applied in opposite way, meaning that the control qubit won't be changed, but the yeah, and then yeah, so because the second qubit is the control qubit, and then first qubit should be changed by using this rule, which means that it should be A XOR and B A, which comes from here, right? So now what we know is that because this is XOR, and the XOR operation is commutative, meaning that we can change the order of the operation. So that means that it will be, it can be also represented as this way. Now, one more important factor is that this XOR operation is also associative, meaning that the order of the operation can be changed, or yeah, like this one. And then, yeah, do you know the result of this one? Because even though we don't know the value of a value, we always know that these two values will be the same. So XOR of the same variable means that it will be always 0. So this is 0. And then the XOR of two value, but if one of the value is already 0, then we know that the result is simply B, because either B is 0 or 1, then the result will be the same as the B value. So the entire operation, entire value of this one simply becomes B, like this one. So yeah, this is the result at this position, and then what happens in the final result? In that case, what happens is that now we are using the first qubit as the control. So yeah, the first qubit just goes the same, and then now what we have to do is B A, and we have to put the B XOR B. Now, yeah, we can again, yeah, they can change the order and then use the associative property, so that B plus B XOR B will be here, and then they will become 0 again, and then the overall value will simply become A, right? So that's exactly what happened at the last stage. So this is exactly what we wanted, because we started with the AB value, and then the final result is BA value, and then the result is independent of actual qubit information stored in each of each of these gate. And then finally, I want to also point out that there is simpler notation, because writing down the three CNAC gate is too much of the effort. So yeah, typically if you see this kind of expression, then this means that it is a swap gate. So yeah, this example implies a lot of things. And then yeah, one thing I want to emphasize is that the concept which was typically used in the computer science is directly applicable in the quantum circuit. So if you are familiar with the programming, then yeah, there will be also a lot of benefit in the design of the algorithm or the circuit. But I also want to point out that the way the quantum logic works is different from the classical logic. And then if you are an expert in the classical logic, sometimes it is actually working against you, because it will somehow limit your imagination. And then sometimes to develop the better quantum logic, then you have to think outside the box. So yeah, depending on your situation, yeah, you should be careful, because the expert in the classical computing does not necessarily mean that you will be good quantum programmer if you don't recognize the important difference between two logics. If we continue the comparison with the classical circuit, yeah, one of the important thing is that when you learn the digital logic for the first time, typically you learn the combinational logic first, and then you learn about the sequential logic. And in the sequential logic, what we generally learn is that there is some kind of flip-flop or whatever register, and then we would have some kind of combination logic, and then the result, and yeah, there might be some result, and then finally they will go back to the this value will go back to the this register for the next step. And then this kind of loop is not allowed in the quantum circuit, because there is no such kind of concept in the quantum mechanics. However, if you want to implement similar function like this one, then we can also use the concept which we generally use in the computer architecture. If you remember that in the computer architecture, even though the um, microprocessor generally works in this kind of feedback loop, but in principle, you can um, expand or unfold such kind of loop by using the concept of this kind of different time. So yeah, at time t and time t plus 1 and time t plus 2 and so forth, and then we can just put additional the same logic like this one, and then goes like this one, and then the result of time 2 will go to another circuit like this one. So in principle, you cannot implement directly the loop, but the function can be implemented by just unfolding the loop part. And then because this kind of loop is not allowed, we say that the quantum circuit is acyclic. Another important fact is that no fan out is allowed. What do I mean by fan out? You probably know that when we are designing some kind of digital logic, something like an AND and OR gate, and then we might combine the result of this one with some kind of AND gate, but that's not the only way we do. And then yeah, we might also reuse the same output value of each of the previous stage to the another gate or something like this one. This is perfectly fine with the digital logic, but this is not allowed in the quantum logic, because in quantum logic, the copy of the information is not allowed, which is surprising. And then I will work on this part in more detail in later slide. But because because of that information in general cannot be copied, so you cannot directly implement this one. And then still there is some way you can implement similar effect like this one, but yeah, you can, yeah, again, yeah, you cannot just have this kind of single wire cannot be feeded into more than one um, yeah, more than one gate simultaneously. So yeah, such kind of situation is called as fan out. And also, opposite way of fan in is not allowed. Fan in is the opposite concept. Yeah, and then in some of the circuit, you can actually directly combine these three wires together, and then depending on the type of the gate connected to the next one, even this kind of connection is allowed. And then yeah, in typical case, this one is used to implement effective OR gate. And then this kind of situation is called as fan-in. And then of course, this kind of situation is not allowed because um, the all the gate in the quantum circuit are should be um, unitary operation. And then the important property of the unitary operation is that it should be reversible. So, and then we know that if we have this kind of fan-in, then there is no way we can implement the reversible gate, reversible operation, because then, yeah, if this was related to something like OR gate, depending on the value, even if you have the value of 1 or true, then you cannot know what should be the original input should be. Yeah, so yeah, there is no way you can reverse this kind of situation. However, you will also, I will also show you that in principle, you can implement the action of the OR gate using the reversible gate. Of course, in this case, it is something like we still keep, yeah, even though it is not fan out, yeah, somehow we keep the original information together with the result of the gate operation. So by keeping this, you can, in principle, implement the effect of the AND gate or OR gate or whatever digital gate you can imagine. And yeah, more you already learned about the controlled NOT gate, and then the generalized gate of the this controlled NOT gate is generally called as a controlled U gate. And if you remember that the controlled NOT gate can be the action of the controlled NOT gate is that only when the control qubit is 1, then we are flipping the value stored in the target qubit, and then to flipping the target qubit is actually equivalent to the action of the X gate. So yeah, instead of using this notation, people frequently also use this notation because the reverse the NOT operation here is equivalent to X gate in the quantum gate. And if we generalize this concept, then in principle there is no reason why the control gate should be applied to the X gate, but it can be applied to Z gate or even Y gate. Yeah, yeah, and then moreover, the gate, the conditional gate doesn't have to be a single qubit gate. It can be some other more complex multiple qubit gate. So this kind of notation means that whether this unitary operation will be applied to this target qubit group or not is determined by this control qubit. So that's that is what this notation means. And finally, you'd also see this kind of symbol frequently, and this means that even though the input might be a superposition of different bases, um, this means that we are measuring at this point in the circuit, and then before the measurement, the quantum, the state stored in this qubit will be quantum state. However, once the measurement is done, then we know that the measurement result cannot be changed. So, and then, yeah, that value behaves more likely classical value. So to distinguish the quantum state and the classical value, we use different notation for after the measurement. So if you see these two lines, then this means the classical value. And then if you see only single line, then this means the quantum qubit line or qubit information. In the previous page, I said that no fan out is possible because no fan out is possible because the qubit information cannot be copied. And then if you look at the action of the CNAT gate, then some people might consider that, well, can the CNAT gate make a copy of the qubit? And the answer is no. And then let's see why it is the case. Well, let's start with some original information stored in the first qubit. Maybe you can call this one as A and the B qubit. Then at this point, the state of the quantum state can be represented by this expression where the psi is this value, this qubit, and the second qubit is in the zero state. So I might just say that this is A and this is B. Like this one. And then at this point, we can also, because the entire state is here. So if we apply the distributive law, then the state can be easily expanded in this situation. So here it is A, B, and this is A and B. And the next thing is, if I apply the CNAT gate between these two, then this is the control qubit and this is target, control and qubit, control and target. And what happens if I start with 0, 0, like this one? Then, because the control is 0, nothing will happen to the B. What about this case? If the control is 1, then this qubit will be flipped. So the result will look like this one. So it goes to here, and this state goes here, and then this state goes here. So if you just look at this one, well, it looks like the first qubit A was 0, and then B is 0, and then the A is 1, and the B is 1. So is this the copy of the this state? No, because when we talk about copy, we don't want this kind of situation. Yeah, this is AB and this is AB, and this is not what copy means. What we mean by copy is each of the A qubit and B qubit will be in the same state like this one. So if I express such kind of situation, then A qubit and B qubit should be the same like this one. And then again, this is A and A. Oops. And this should be B and B. So this is what we want. And is this expression the same as this one? Of course not. So because if we expand this, then it is alpha squared 0, 0, and then there are 4 terms while there are only 2 terms. So this was not the copy. So can the CNAT generate this result? Of course not. So maybe some people might suspect that this was only the problem of the CNAT. So maybe we should be able to find out some more generalized gate which can copy this situation. And of course, it is not the case. So I will prove that it is not possible. And then such kind of theorem is called as no cloning theorem. The proof of the no cloning theorem goes in the following. So we will use the proof by contradiction. So let's assume that there exists a cloning machine. So assume that for the time being, let's assume that cloning or copying is possible. Then still, even the cloning machine still should follow the quantum mechanics, because we are basically assuming that quantum mechanics governs the entire world, meaning that everything should be explained by the quantum mechanics rule, and then this machine should be still this copy machine still should be should follow the quantum mechanics rule, which means that it should be unitary operation. So let's say that we start with some kind of um, qubit information, and then the final result, we want that there will be the copy of the same quantum information like this one. And then in this case, we need to start with some additional qubit, because we know that um, any any unitary operation cannot increase the number of qubit. So we should start with the same number of qubit like this one. So this initial state is the kind of placeholder or variable or memory to hold the resulting quantum state. So yeah, we are assuming that such kind of machine exists, and then such kind of machine can be modeled as a unitary operation. And mathematically, we can write that if this kind of operation is possible, then that means that if we apply the unitary operation corresponding to this cloning machine, then they will apply in this way, and then the final result should be like this one. So, and then, yeah, we don't know what kind of initial state we should start, but it is obvious that this initial state should be constant. I don't know what kind of state it should be, but we somehow allow that this can be arbitrary state, and then arbitrary but constant, because that um, this this machine still works even for any kinds of input state. So yeah, let's start with some easy copying. So let's say that we might start this psi can be just a simple 0. Then yeah, based on this rule, the result for this copying should behave like this one. What about the one case? Well, it should behave like this one again. The question is, what happens if we use some arbitrary superposition of 0 and 1 for this state? Yeah, so this is the arbitrary state corresponding to psi. Then, because we say that the cloning machine should be modeled as unitary operation. So this is again unitary, and then one of the important properties is that unitary operation is linear, meaning that if I expand this one as a alpha 0 tensor init plus beta 1 tensor init, then the U operation should be applied to each of the terms. So yeah, eventually it should be represented in this way. And now we know that we already obtained this result corresponding to this one. And then for this case, alpha is simply a complex number. So it can be just pulled out of here. And then that means that U is applied directly on the entire state, which is exactly like here. So what should be the result of the application of a U on here? It should be like this one. And similarly, U will be only applied, U will be directly applied on the one tensor init, which, and then we know the result of such kind of operation like this one. So if we combine those results together, then the result should look like this one, right? Yeah, because alpha is pulled out of this operation, and the beta is the same. Is this what we are expecting? Well, we expect that if we provide our input state as a alpha and beta linear combination like this one, then we expect that the same quantum state, alpha 0 plus beta 1, is also reproduced in the second qubit. So this is what we expect. But what we obtained is this one. Is this state the same as this one? Of course not, because if we expand this state, then there will be 4 terms and summation of 4 terms, and then even for the first term, which is the 0, 0 basis, it will be alpha squared, while here is only alpha, and then the final the 1, 1 combination will also have a beta squared, while this is beta. So even if we started with the assumption that there exists a cloning machine, and then we generalized, we allowed any arbitrary possibility, but the result is that we will obtain this kind of contradiction. So yeah, by proving the contradiction, we show that there cannot be such kind of cloning machine. So that's why we call this kind of situation as a no cloning theorem. And this is astonishing because this means that in digital domain, you can copy any of the information. However, in the quantum mechanics or in the quantum information, you cannot copy. Sometimes such kind of property is very helpful because we don't want to lose our, we don't want someone else to copy the information we currently have. So such kind of the advantage of no cloning situation can be used for the cryptography. However, for the computation purpose, no cloning is not helpful because you will learn that in the with the many of the quantum algorithm, you might yeah, at the end of the calculation, you will be left with your solution. But the solution is represented as a superposition. And unfortunately, you can measure only one of them. And then once you measure them, then the state, quantum state will collapse, and then you cannot obtain all those other information. But you have to repeat the same calculation over and over. So that's there is a cons and pros with the no cloning theorem, but you should be careful when you are dealing with the no cloning when you are dealing with the quantum information. With the no cloning theorem, there is one point which I really want to emphasize. When you just hear about the no cloning theorem, then you might get the impression that there is no way to make the same quantum state twice, or multiple qubit can have the same type of the quantum state. That's not true, because you know that if you have the horizontally polarized light, then you can have another photon which will have the exactly the same. And then even when this horizontally polarized light goes through the something called as a wave plate, then in principle we should be able to create this kind of superposition state. And then if you know how to create this one already, then you might start with another photon and then pass through the same device or the same component, then you would obtain exactly the same quantum state. So what does no cloning theorem really prevent or really allows? Well, no cloning theorem says no cloning theorem is true when you are given only the final result of this kind of superposition. So yeah, the guy who made this state does not tell you how this state was created, and then he or she will only tell you that it was the superposition of these two state. Then there is no way you can reproduce this kind of situation either quantum mechanically or classically, because you might just think that, well, if it is a superposition, we can just measure it and then try to reproduce this situation. The problem is, if it is already in a superposition, what happens if you measure? You will only measure H or V. And then let's say that if you just measure the H, what happens to the result of the, what happens to the original qubit state? It will collapse to H. So if you keep repeating, then you will continue to measure H. However, it's not the true state of the original state, because we know that it was originally superposition of these two possibility, and then you just happen to measure H. And then that doesn't tell you anything except that alpha is not 0. But we don't know whether alpha is 1 or 0.5 or zero point 0.1 or 0.001 or whatever. Yeah, that does not give you any further information. So that's exactly what the no cloning theorem says. So if some guy prepared this quantum state, but that guy doesn't tell you how it was created or what kind of quantum state it is, then there is no way you can reproduce the same exact quantum state in the next qubit. So that's the meaning of the no cloning theorem. So don't get confused when you are thinking about the possibilities. Up to this point, we only considered measuring some given quantum state in terms of 0 and 1 basis. And then we generally call 0 and 1 basis as a computational basis. However, we know that in quantum mechanics, where the third postulate say that uh, um, um, the each of the measurements generally has a corresponding measurement operator, and then in principle, depending on the definition of the measurement operator, we can measure them in different bases because measurement result generally corresponds to the eigenvectors of the measurement operator. So in principle, we should be able to measure in different bases. And then, for example, if we are given some arbitrary quantum state, how can you measure in the different bases like this basis, 0 plus 1 basis or 0 minus 1 basis? These are the good also normal basis because you can calculate, you can check that this basis has the length of 1 and they are the same also. So both of them are normalized. And then if you multiply, if you calculate the inner product between these two vectors, then they will just vanish. So yeah, they are orthogonal to each other. So these are two orthonormal bases. And then in these using these bases, you can the measurement in these two bases are very good measurement. Then how can we how can you measure in these spaces? Or the first question is, what is the meaning in the measuring in different bases? Well, if we are given some arbitrary basis, then in principle we can re-express this state using different bases. How can you calculate such kind of result? Well, yeah, you know that if we define plus as this way and minus in this way, we can also calculate that zero state should be the summation of these two vectors, and then it is if you calculate the square root of 2, then zero can be obtained. And similarly, if you calculate the difference between a plus and minus state and then divide by square root of 2, then you will obtain one state. So yeah, this is the important relation between the 0 and 1 0 1 basis and plus minus basis. And then you can just plug in this definition, this relation to each of them, then you will obtain this result. And then if you just collect all the terms with the plus and minus term, then you would obtain this kind of situation. So measuring in different bases like plus and minus bases means that you just re-express the original quantum state using those spaces. And if one of these coefficient or the probability amplitude becomes 0, then here in your measurement you will only obtain only one of them. And then if they do, none of these probability amplitude vanishes, then you have a chance to measure each of them, but the probability to measure plus or minus depends on the absolute value of this part. So that's the meaning of the measuring in different bases. Then how can we implement such kind of measurement in polarization? Well, for the polarization, there are two options. One is, yeah, if you remember that there is something like um, polarizing beam splitter, then the one option is, if we have some photon coming in and then it is leaving here, and then depending on it, and then generally this polarizing cube has this kind of configuration. So depending on the input polarization, either it is H or V polarization, H polarization will transmit, while the V polarization will be reflected between this inner surface. So this is the sorry. This is what happens. So if you want to measure them in terms of the HV basis, typically we represent this one as a HMV basis, then you would just use this polarization, and then this is called as a polarizing beam splitter. And then if you want to just measure in HV basis, then you just use the PBS in this orientation. However, if you want to measure them in the along the um, DA basis, yeah, diagonal anti-diagonal basis, then what you can do is rotate this one by 45 degree. Then the definition of the H and V will be swapped, and then um, the transmission will be either well, that depends on how you which angle you rotate, and then how you define the definition of the HMV. But the transmitted light will be will be let's say this corresponds to anti-diagonal, and then the reflected light will become diagonal. Yeah, so that's one option. But there is actually another option. Instead of rotating the PBS by 45 degree, what we can do is put something called as a wave plate, and then the role of the wave plate is that it will rotate the original input um, input um, polarization into another one. So for example, it can rotate the V to D and then horizontal to anti diagonal direction. So after the rotation, yes, so yeah, H will become here, yeah, it will become anti-diagonal, and then the well, yeah, I yeah, sorry, yeah, I should say in the other way. Sorry. Um, yeah, you might consider that it is rotating the V and H, but on the other hand, you might also consider that it is rotating the A to H and then D to V. So initially, when it is entering here, then it was you might consider that they are the um, anti-diagonal and diagonal, which is tilted, and then after it is transmitted through the wave plate, they would become like horizontal, and then this will become vertical. Yeah, so that's another way with the polarization. And then instead, without rotating the PBS, in principle, you should be able to measure in A and D basis, because after it is transmitted through the this plate, then they map to the H and V basis. And then if you started with the superposition of these bases, then the result will be still the same superposition. So yeah, before the transmission, the psi might be alpha A plus beta diagonal. Then after the transmission, they will still remain as the superposition of these, but the basis vector is replaced by H and V. So just measuring in this space using this PBS with the HV basis, it is equivalent to measuring the original state in the A and D basis. So yeah, those are the two options for the polarization. But what happens? What can we do with the atom? Yeah, let's say that we also learned that the qubit can be implemented two-level atom, and then in this case we have two quantum state, and then we want to sometimes we want to measure them in terms of this plus spaces and the plus minus spaces. Then what do we mean by measuring in the plus minus spaces for the two-level atom? Well, that might be a little bit confusing. Do we actually mean that when I said that measuring the 0 and 1 in the two-level atom, that is kind of corresponds to measuring the frequency. Yeah, so I mentioned that each of the energy has its corresponding frequency. So do we mean that measuring the frequency in the plus minus basis? So then if we measure the plus basis like a 0 plus 1, do we get the average between these two? While when we measure the minus, we are measuring the difference frequency? Of course not. That's not the case. So what we, if you want to measure in the plus minus spaces, then what we should do is we should do something similar to this one. So there is some kind of physical operation or physical process which will transform zero state into the superposition of 0 plus 1 state. And then the same process also changes the one state into the 0 minus 1 over square root of 2 state. And such kind of process is generally called as Rabi oscillation. And then, unfortunately, I don't have enough time to explain the details of the Rabi oscillation, but you can just trust me that we can implement this kind of rotation, this kind of um, change linearly. And then if we apply such kind of Rabi oscillation, then the basis will be transformed in this way. And then what happens is exactly like measuring in this basis. So if you think about this situation, then with the application of the Rabi oscillation, or in more general case, we in more general term, we can say that it is basically equivalent to applying the Hadamard gate before the measurement. Then it is corresponding to the change of the measurement basis. And then once we, if you think about rotating this polarization linearly, then the application of the Hadamard gate can be understood physically. And then once we apply such kind of gate, then we measure. Then it is equivalent to measuring in the plus minus basis. So when do we need such kind of measurement in other bases? Why just we cannot measure it in the 0, 1 basis or computational basis? Well, one of the example we already saw was that we wanted to find out the relative phase, and then that was helpful. And then another application is what we are going to cover in the next lecture, and then it is called as something as a quantum teleportation. And moreover, in the during the quantum computation, or in many of the quantum algorithm, the there are a lot of operations, but many of them actually corresponds to the basis rotation for the gate for the measurement. So sometimes it might not be obvious that it corresponds to basis measurement, basis rotation, but all the unitary operation also corresponds to basis rotation. So if you think about such kind of situation, then the entire algorithm can be just considered as the measuring in different bases. Well, yeah, we can get back to such kind of point when we discuss the quantum algorithm in more details. As an extension of the discussion in the previous page, let's also talk about something called as a Bell basis. And then the Bell basis, the motivation for the Bell basis is the following. Well, yeah, let me first show you what does the Bell basis look like. Bell basis originally, you can when you see the Bell basis for the first time, then it might be very confusing. But let's think a little bit from a little bit different perspective. Let's assume that we have two qubit, one A and B qubit, and then we know that there are two combinations for the A and B qubit. Sorry. One will be A qubit can be either 0 or 1, and then the B qubit also can be either 0 or 1. So yeah, there are all four combinations which we already know too well. Yeah, so these are all the possible combinations. And if you remember how we discussed the relation between 0 and 1 basis, then we can also consider plus space, which was the summation of the 0 and 1, and minus space, which was the difference between or 0 minus 1 state, something like this one. So one thing we can consider is we can combine, first of all, these four tensor product vectors are also normal to each other. And then in this case, we can first think about combining these two also normal bases. Then one thing we can try is to add these things together, or we can subtract them together. And then for this case, we might also prefer to have the normalization. And we only used these two, and then we can also combine these two together, and then these can be also combined in 0, 0 plus 1, 1, or 0, 0 minus 1, 1, something like this one, and then with the same normalization. So this is the definition of psi plus and psi minus state. And then if you remember how they were combined, then psi means that the two components are each of the term are different. 0, 1 or 1, 0 type. So for those cases, we call them as a psi. And then you know why they are called either plus or minus. They are just a sign here. And then if the each of the term are the same, 0, 0 or 1, 1, then we call these things as a psi plus phi plus and minus. So why do we call these as a basis? Well, for something to be a good basis, or then we should first check whether each of these vectors are orthogonal to each other. And then we know that for if you recall this combination, if we have two orthogonal bases, then the summation of those two, or and then the um, um, subtraction of those two are orthogonal to each other. So yeah, just by having, yeah, and then we know that these two are orthogonal, where each of them are orthogonal to each other. So these are also orthogonal to each other. And then if we just add them and then subtract them together, then they should be also orthogonal to each other. Similarly, these two are orthogonal to each other. So we know that these are orthogonal to each other, these are orthogonal to each other. Then what about between these two groups? Well, we started that each of them are orthogonal to each other. So each group are composed of these two pairs and then these two pairs. So yeah, combination of these and combination of these. And then because we know that each of the group, and not only the each of the group, but each of them are orthogonal to each other. So there is no reason why this group should not be orthogonal to this one. So this is orthogonal. And then by adding the by dividing by square root of 2, we normalize each of the vector. So even though this combination looks very um, weird at the first time, yeah, they are actually also normal to each other. And then we can say that they are complete bases because um, these four bases exist in the new vector space created by the tensor product of these two qubits, or combining the vector space corresponding to two qubits. And then we know that the dimension of the new Hilbert space or tensor product space is 4, because we know that the entire Hilbert space can be spanned by these 4 combinations. So and then we know that these 4 orthonormal vectors are um, 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 also these 4 vectors are orthonormal to each other, and there are 4 of them. So that means that because this one has the same dimensions as these 4 bases, so um, any arbitrary vector in this space, or the tensor product space generated by these two qubits, any vector in that space can be also expanded in terms of these four basis vector. So yeah, again, yeah, these each of these look a little bit weird, but these are very good bases, and any arbitrary function, any arbitrary vector can be represented as the linear combination of all these 4. So and this basis has a special name. Sometimes it is called as Bell basis, or Bell state, and then sometimes it is called as EPR state or EPR pair. And there are many names for this same basis. EPR means the name EPR came from the um, 3 physicists named Einstein, Podolsky, and Rosen. These 3 people, not only these 3 people, but a lot of people did not believe in the quantum mechanics. So yeah, at least these 3 people had the discussion of how to disprove the quantum mechanics, and then they came up with some weird state, which is now known as the entangled state. But at that time, yeah, they didn't have any name. So yeah, people used to call this state as a EPR state. And then yeah, and then yeah, the main purpose of such a state was to show that quantum mechanics does not make sense. However, after several tens of years, Bell, yeah, this is different from the Graham Bell who invented the telephone. Yeah, this is the physicist John Bell, and then he came up with an idea about um, he proposed some experiment so that whether the claim of the EPR claim is correct or not. And then yeah, and then eventually, yeah, some people came actually did the measurement, and then they showed that EPR assumption is wrong, and then there exists this kind of state. So that's why it is sometimes also called as a Bell basis. Well, most of the time people call this one as a Bell basis. Then the next question is, how can we create the Bell basis or Bell state? Well, it is actually quite simple. Yeah, all we learned about the Hadamard gate and then Sinner gate. And if we just by combining these two gates, we can create the entangled state. Yeah, for example, if I start with the zero state for the A qubit, and then zero state for B qubit, then right after the Hadamard gate, the A qubit will become uh, as the summation, sum of these two factor, but at this time it will be still zero. So the state at this point can be expressed as zero, and then this can be also expanded as 0 0 plus 1 0 at around at this point. But after the Sina gate, this state should become square root of 2 0 0, because if the control qubit is 0, then it won't do anything for the target qubit, so it will be 0 0. But if the control qubit is 1, then it will actually flip, and then the target bit is 0, so it will be turned into the 1 1. And then you can see that if we have 0 0 for the A qubit, then the difference for the B qubit B is that well, if this one is 1, then this second qubit value will be 0, will be opposite, meaning that if this was 1, then it will be 0 1 and 1 0. And if we had 1 instead of 0, then this sign will be negative, and that negative sign will appear here. So overall, this is the kind of result. So yeah, again, if I started with the 0 0, then we would obtain 0 0 plus 1 1. While as I mentioned, if we had a 0 1 combination, then the second qubit will be opposite, and then if we had 1 instead of 0 here, then this will be minus. So the only difference between these and these are only the sign. So this is the result of this circuit. And then why do I show this result? Well, as I mentioned, any arbitrary state can be either expanded as the linear combination of these four basis vector, which is called as a computational basis, or any arbitrary state can be also expanded as the linear combination of these four basis vectors. And then sometimes we actually want to measure some state in this basis rather than this computational basis. And if we want to measure in these spaces, that is possible because we know that any type of measurement has its corresponding eigenvector, or any measurement has some Hermitian operator, and the Hermitian operator has its own eigenvector, and then right after the measurement, the final state will be one of the eigenstate. So even if you have the and then these four pair bases are very nice complete bases, also normal to each other. So in principle, we can also do the measurement in these bases. The problem is it's not easy, or it's not straightforward to measure in their bases. So how can we measure in the bare basis? Well, if you remember how we measured in this plus minus basis, then what is the solution for measuring the two-level atom in the plus minus basis? Instead of trying to measure directly in these spaces, what we did was transform the original basis, 0 and 1 basis, into the plus and minus basis. And then once we transformed, then measurement in the computational basis eventually corresponds to the measurement in the plus minus basis. So yeah, if we use such kind of concept in the bare basis, what we can do is also similar to this situation. So I shows you that all the computational basis can be transformed to one of the bare basis, and then we know that these are the unitary transformation, well, meaning that um, all the gates are the linear operator, and then combination of the circuit means that then these are the combination of the unitary operation, and then the overall result is the unitary operation. And the most important property of the unitary operation is that it is reversible. So instead of applying the gate along this order, if we apply the gate in the other order, then it is a reverse process. And then in principle, we can, by going from here to here, we can map each of these four well bases back to the computational basis. And that is what is shown here. So yeah, I just reversed that circuit. And then yeah, if we go through this one, then we know that each of the phi plus minus, psi plus minus will map to different computational bases. So yeah, before we measure, if we just apply this, I call this circuit as an unentangling gate. So by applying the unentangling gate, I map each of these special bases back to the computational basis, and then just the measurement in the computational basis will eventually correspond to the measurement in these special basis. So that's how we can measure in the bare basis. The reason I'm explaining the measurement in the bare basis is it is the most important part when we are discussing about the quantum teleportation, which will be the topic in the next lecture. So yeah, I will continue about quantum teleportation in the next lecture, and then yeah, I will stop here today.